All right, guys. Here's what I need you to know from what I missed on Monday. Okay? So we essentially are starting. Why are we not working? All right, let's try that again. Here's what I need you to know about Chapter 7 that you may have missed. All right, so some of the stuff that we did from Chapter 7, periodic table. We started with Coulomb's law. You do not need to use this law quantitatively. That means you're not going to have to plug numbers into it and solve for it. But you do need to know that the force between two things that are charged, so in this case, because we're talking about the periodic table, between the nucleus and an electron is going to be related to some constant, which doesn't matter, times the charge on each one over the radius. And I don't really care that you know that the radius is squared or not, because in the POGL that we did, it was not, right? It was just the energy, which for those of you who have taken physics, force times distance is a form of energy. This is what you need to know about Coulomb's law. You need to know that as your charge increases, the force increases. So if the electron's charge is not really going to change in this case, there are other applications for Coulomb's law, but as the charge on the nucleus increases, then the force between the nucleus and the electron increases. The other thing that you need to know is as distance increases, the force between the nucleus and that electron, as that electron gets further away, decreases. When in doubt, if both things are changing, which is going to be rare, charge wins, okay? And a couple people ask me like, well, radius is squared, so why wouldn't distance win? Because the charge we're talking about is going to be like +1, +2, +3. Like, so the difference between +1 and +3, that's triple. Whereas when we're talking about the radius, we're looking at like 170 picometers to like 180 picometers. And the difference there is not nearly as much as that charge is going to really be affected. So we need to talk about nuclear charge, okay? So let's do this, and we'll go here. All right, nuclear charge. Nuclear charge is literally the charge on the nucleus. That's a Mrs. Bell definition, okay? So if I have two things, I've got sodium and I've got potassium, I'm going to draw them, okay? I'm going to talk about their nuclear charge. I'm going to draw like a terrible drawing for it. So there's sodium is atomic number 11, so its nuclear charge is positive 11, because the only thing in the nucleus that's charged are those protons. Then we've got 3 shells, right? And they don't really look like this. They're way cooler, but this is what we're drawing them to look like. And potassium is number 19. So there's its nucleus, and potassium has 1, 2, 3, 4 shells. Not my best drawing, but it's all right. Okay, now here is sodium's valence electron, and here is potassium's valence electron. Okay, so the nuclear charge is +11 for sodium and +19 for potassium. But, okay, the difference here is that there are a lot of forces acting on that valence electron. This valence electron is pulled in by that nucleus, okay? But you have to remember that there are 10 other electrons here. And I'm going to draw them. 4, 5, 6, 7, 2, 3, 4, 5, 8. So those are those other electrons. Now, all of those electrons are essentially repelling that valence electron, right? Because like charges repel, and we learned that with the POGL that we did. So the nuclear charge that sodium feels is the true nuclear charge is +11. The true nuclear charge for potassium is +19, okay? But potassium has 18 electrons that are repelling that outermost electron, okay? So since there's so many different interactions here that we don't really need you to take all of them into account quantitatively. We want you to think about this concept called, ooh, I didn't know I could do that. Look at that. Okay, come on, guys. There we go. We're going to look at this concept called effective nuclear charge. I know I spelled it wrong. I'm sorry. It's been a long day, guys. An effective nuclear charge is going to be the same as the number of valence electrons, and I'm going to show you why. It's the same as the number of valence electrons because think about this sodium electron right up here, this valence electron, that's the outermost shell. That sodium atom is attracted to the nucleus with a charge of plus 11, okay? But it's repelled by 10 individual kernel, which means non-valence electrons, okay? So it basically has a force in of 11 and a force out of 10. So the effective nuclear charge that that valence electron feels is positive 1. Okay, it's the same as your number of valence electrons. The same thing is true over here, okay? I've got this potassium. It has 1 valence electron. There are 18 kernel electrons, or electrons that are in the middle there. Those 18 electrons in the middle are the ones that are repelling that valence electron. So it also feels an effective nuclear charge of plus 1. So you'll notice that even though potassium has a greater nuclear charge than sodium, the effective nuclear charge on those valence electrons in that same column is essentially the same, okay? But when you go across a row, when we're looking at like the difference between lithium and fluorine, for example, okay, lithium has 1 valence electron, so lithium's nuclear charge is positive 1. Effective nuclear charge, I'm going to call that EFN, or sometimes you'll see it as ZEFF, okay? And fluorine has 7 valence electrons, so its effective nuclear charge is plus 7, okay? So you can see that the difference across a period is that the nuclear charge is significantly increasing, okay? So your nuclear increases across a period. And really, that's true for nuclear charge and effective nuclear charge. But when you go down a group, which is what I did here, the sodium to potassium, your nuclear charge might be increasing, but you've got other factors going on. You have this extra shell of electrons. And that extra shell of electrons repels, it counteracts any additional thing that those extra 8 electrons might have, any additional force. So your effective nuclear charge is the same. So what you're looking at here is, since your charges are the same, what's your big driver as you go down a column? Let's do this. It's, oh wow, here it is. Nope. Okay, well, I don't know where it went, but it is distance. You're getting further away because there's more shells of electrons. All right. The last thing that I really wanted you to get from what we did on what you were supposed to watch in class on Monday was ionization energy. All right. Ionization energy is going to be the energy required to remove the outermost electron. Sorry, guys, my handwriting is worse on my iPad than it is on the smartboard. Okay? And you found when you did the POGL that it is equal and opposite to V, which was the potential energy, right? So the potential energy of the electron. So the electron is held with a negative potential energy. That means it's an attractive energy, right? There's an attraction between the electron and the nucleus. And in order to remove that electron, you're essentially moving it to a distance of infinity, right? So you have to put in at least the amount of energy that it's held on by so that you can make that net energy 0, and then you can move it to a distance of 0. So a distance of infinity, which would make your potential energy 0. Now, as you go down a group, okay, that's like group 1, group 2, group 3, the ionization energy is going to decrease because of added shells of electrons. This is distance. This is the distance part of Coulomb's law. Your effective nuclear charge is the same. It's plus 1 in group 1. It's plus 2 in group 2, okay? Your effective nuclear charge is the same, but your ionization energy is going to decrease because that outermost electron, remember it's the outermost electron, is getting further and further from the nucleus. So Coulomb's law says that your force is going to decrease. As you go across a period, your ionization energy is going to increase because of your increased nuclear charge. Okay? As your nuclear charge increases, the charge increases, okay? And the distance doesn't change too much appreciably. Well, we're going to learn about that tomorrow. So your nuclear charge is getting stronger. So it's going to take more energy to remove that electron because it's going to have a more negative potential energy because the charge on the nucleus is greater, okay? Here's what I want you to think about, okay? Here, when you're constructing explanations for this, okay, this unit is very much unit construct a good explanation, right? And we, what you might have used in Regents chemistry is not necessarily going to fly in AP chemistry, okay? So if I ask you to say, okay, neon has a greater ionization energy than, let's just scribble there, why don't we? Fluorine, because, okay? That is true. Neon has a greater ionization energy than fluorine, and it's really something that the AP exam is probably going to tell you, okay? They're probably going to tell you and then ask for a reason why. One reason that kids like to tell me is because ionization energy increases across a period. That's a hard no. That's an effect. It's not a cause. That's not a because, okay? Ionization increases across a period. Why does ionization energy increase across a period, okay? Don't tell me that ionization, your trends are not reasons, okay? Trends are not reasons. All right. Another answer that kids really love to give me is that ionization energy, neon has a greater ionization energy than fluorine because neon has a full valence shell and therefore does not want, I literally said that, yes, does not want to lose any electrons. Guess what, guys? Neon is an atom. He has no wants, needs, or feelings, okay? So just because neon has a full valence shell does not mean it's automatically harder to remove an electron, okay? Neon has a greater ionization energy than fluorine because neon has a greater nuclear charge. Perfect explanation, I'd like you to reference Coulomb's law. Okay, what I'd like you to do is I'd like you to say neon has a greater nuclear charge, and due to Coulomb's law, that indicates that the energy required to there's a greater force. How about that? A greater force or a greater energy between the nucleus and its outermost electron. Something along those lines I would like the best. Those other two are not explanations, okay? They're more effects. They are not causes, and we're really looking for what is the reasoning behind it, okay? That's what I really wanted you to get out of Monday. Maybe you did, maybe you didn't, but hopefully this helps. Thanks.